Alright, so welcome back again. This is my second time at posting this 2.4 video since the audio didn't work last time. I think what I'm going to do from now on is just upload these things to YouTube because that seems to work better. Okay, and I also uploaded 2.1 to YouTube. That one sound worked fine. 2.4, since I converted it on my computer to an MP4, it didn't save the sound, and I deleted the original. So we're going to see how this goes. Alright. So 2.4, solving right triangles. And this is kind of the meat of trigonometry, I would say. Solving these right triangles. So we will continue to do basically this all semester. Yeah, I mean, it just comes up over and over again, these techniques. Before we actually get into it, though, just a word about significant digits. These are a way of measuring or judging the accuracy of a measurement, and they only apply to a measurement. So other things like counting numbers or numbers derived theoretically, or I say theoretically, things like pi, the number pi, it's a ratio of the circumference of a circle to the diameter, but that is it's a I guess we call it a theoretical value. It's a fixed exact value. We don't take into account those significant digits, and I'll talk about that in one of our examples here. But first, the basics. The easy way to do this is to count. If you're given a number, you're asked to find the number of significant digits. We count any integer between 1 and 9, or any digit between 1 and 9. Where the trick comes in is these zeros, because you only count certain zeros. You count zeros that occur between other numbers or other digits, and you count zeros that occur to the right of the decimal place or after the decimal place. So let's look at these examples. We've got 408. That has 3 significant digits because this 0 comes between 2 other digits. We do count that. 400, on the other hand, if this was a measurement, someone said 400 miles, that's not, that we would only say, okay, that's accurate to 1 digit. If they had a better estimate, well, they should have given us that. If they meant it was 400 and not, I don't know, 410, they should have specified that in some way, shape, or form. Okay. 8700, again, only has 2. We only count these 2 digits. We don't count the 2 zeros. Whereas 8700.1 has 5 because these zeros occur between 2 other digits, the 7 and the 1. And finally, 200 or 2.00 has 3 because those zeros occur after the decimal place. So those cover all the basic examples you could see. Just make sure you're comfortable with that. And since I'm going a little quickly today, I'll go ahead and point out, this is a video. You can always stop it, rewind it, etc. This is for your benefit. You can skip to the parts. If you know all this stuff about significant digits, skip ahead a few minutes, and you can get to the part about solving right triangles. Okay, you may have already read this while I'm sitting here jabbering, so skip on ahead. I'll be stuck here in the past waiting. Trying to catch up to you. Okay, so performing a calculation, the result of that calculation is only as accurate as your least accurate measurement. And so we have to use the least amount of significant digits that occurs. So for example, 7.02 times 8.296. 7.02 has 3 significant digits. 8.296 has 4. So our final answer can only have 3 significant digits because the least accurate number had 3 significant digits. And this one had 4 digits. That was more accurate, but we have to use 3 since that's the least accurate number. So we multiply this out, and we actually get a few extra decimal places, but we drop those off. Okay. Now, kind of a side note before we go on. MyLabs Plus, some of the problems will ask you to round to a certain decimal place, regardless of however many significant digits there actually are in the problem. So take that into account. If it tells you to round it to 2 decimal places, even though this example has 3, we can still round it to 2 because that's what we were asked for. Okay, so something to keep in mind. There we go. So let's move on. Now I already mentioned this. These only concern measurements, not counting numbers or theoretical work, like, for example, pi, that has as many digits as you want. You're not going to write that out infinitely, to infinitely many digits. So we're looking at an example of counting numbers. So we've got Jill here, who's calculated the average weight of each of her apples is 5.281 ounces. Somehow she's calculated this. Maybe she just had a tiny scale and she didn't want to weigh all of her apples. I don't know, that's only 13 apples. She probably could have weighed them all. So anyway, she has 13 apples and she wants to know how much they weigh all together. Well, if each one was 5.281 ounces, we could multiply that by 13, and that gives us the number of ounces this thing weighs. So we do that. 5.281 has 4 significant digits. 13 is an exact count, so we disregard that number of significant digits. I mean, you may look, well, clearly you look at 13 and you say, okay, this has 2 significant digits. Well, we don't care. Excuse me. Our answer is still going to have 4 significant digits because she didn't count 13.0 apples, or she didn't. This isn't rounded to any. This is not a less accurate number. It's not like she had some fraction of an apple and she rounded up or rounded down. This is an exact count of the number of these apples, so we disregard the significant digits. So our answer we could still have 4. So we disregard this 13 completely. We go ahead and do our calculation, and we keep 4 digits in our final answer. So we get our final answer is 68.65 ounces. This was in ounces. Now I just thought of this. I probably should have put it in the problem ooh, that's a bad marker. 68.65 ounces. If we were to convert this to pounds, once again, we would disregard the number of significant digits in that conversion factor because that is a theoretical. Actually, it's by definition that this is an exact count. So what? A pound has 16 ounces, right? Well, I hope that's right because I'm going to go with it. So we can use a ratio here. We've got 1 pound is 16 ounces. This is actually a really great point. We don't do a lot of unit conversions in here, but I always like to talk about it when it comes up. This is what I was taught by a chemist when I was in high school, and it's always really stuck with me. I really liked it. We know that there are 16 ounces. Presumably, I'm right here. There's 16 ounces in a pound. We could write a ratio of either 1 pound to 16 ounces. We could have written it the other way. We could have written 16 ounces to 1 pound. Okay. The question is, why did I use this particular ratio? Well, what I wanted to do, I wanted to cancel my units. I want to get rid of ounces and be left with pounds. So this is just a whole number. You know, you can always write a number over 1. I think to myself, okay, I've got ounces on top. In order to cancel it out, I'm going to need ounces on bottom. And that's how I determine what ratio I want to use here. Okay, so that tells me I also want to be dividing by the 16. So let me get a different color here. None of these markers are working great today. So my ounces cancel out. Right, and here I'm actually going to do this division. 68.65 divided by 16 is who knows what. Let's see. 68 0.65 divided by 16. I get that this is 4.290,625 pounds. Okay. Okay, but we only need these 4 significant digits here. So that would be 1. But yeah, 4.291. There we go. Okay. Now where was I? All right. Okay, we just finished this June one. Yeah, that's the problem with doing this during office hours, or not during office hours, before 5. People keep knocking on my door. Okay. So next we're going to go to solving right triangles, which again is kind of the heart of trig, and we'll use these techniques all semester. So let's see. Move this back over. Okay, so to solve a right triangle, we're going to be doing a little bit more than just using the trig functions. We're going to have to bring in some stuff hopefully you remember from geometry. The Pythagorean theorem, for one, and you got to know that the sum of the angles in a triangle is 180 degrees. So that's some other stuff we'll need to know. I'm going to go ahead and just note that before we get going too far. Yeah. Okay, so I've got a right triangle here. This first rule, applies no matter what. The sum of these triangles, these angles in a triangle has to be 180 degrees, even if we didn't have a right triangle to start with. So for any arbitrary triangle, this is true. A plus B plus C has to equal 180 degrees. Now, if we make this a right triangle, then that tells me right away that C is 90 degrees. So I've got A plus B plus 90 degrees equals 180. And I can do a little bit of manipulation to simplify this. So we get that the sum of those two other angles has to be 90 degrees. And you probably already know that, but this will use a decent amount in this. I'll probably just use this. I'll say, okay, well, if we know this one, then I know what this one's got to be. It's got to be 90 minus that. So these are basically the same rule. This one only applies to our right triangle. This applies to really any triangle. What else I wanted to say? These letters A, B, and C, we'll use these a lot in here. When we do that, another common notation is to use a lowercase letter for the sides and the uppercase letter for the angle. I feel like I already explained this in 2.1, but it may have been when I was making the first attempt at this video, so I apologize when I'm repeating myself. Okay, I'm going to use a lowercase b there and a lowercase a there. So again, capital A for this angle, lowercase a for the side opposite. C is a little bit harder. I'll just make this one really large. So there's my angle C, and there's my side C. Okay, so if we've got our labels written like that, this makes it a lot easier to write down the Pythagorean theorem, which says a squared plus b squared equals c squared. So we'll use that a good bit when we're solving right triangles, because sometimes it's easier to do that than to solve another trig function. to find our values here, or to find our sides. Okay. Let me actually just erase this and read. So our first example here, we've been given this triangle and we're asked to solve it. They've told us that they've got it all nice and labeled for us. This one is 34.5 degrees. We're calling this A again, this B, this C. This is our little c, C. 12.7 inches. And those are the only ones we know. This is little a, this is little b. So the question is, how do we find the other sides? What I want to do, I've only got two little pieces of information here. Any one of our trig functions, like for example sine, I'll do this one, yeah. So just to repeat our definition, sine of some unknown angle theta, or sine of some angle theta, is equal to the length of the opposite side divided by the length of the hypotenuse. Okay, so we've got three pieces of information there. We've got our angle, we've got our opposite side, the measure of our opposite side, and the measure of our hypotenuse. Okay, so and the sine is a function that we do, or an operation we're going to perform on this, kind of like an operation. Just like squaring something is an operation. Sine is just something that we're doing to this. Sine is not so much a thing unto itself. It's a function of some variable here. So we've got our three pieces of information. We can solve this for any one of these pieces of information. So for example, if I wanted to solve it for the opposite side, I could do that really easily. I'm going to introduce another color here to make things crazy. So if I wanted to solve it for the opposite, I could do that pretty easily. I'm dividing my opposite side by the hypotenuse, the length of the hypotenuse. So if I multiply both sides by the length of that hypotenuse, look at that, it canceled out my hypotenuse. So now I've got this thing solved for my opposite side. The length of the opposite side is equal to whatever the hypotenuse is times the sine of whatever my angle is. So if I know the hypotenuse and I know one of my angles, I could then very easily calculate the opposite side. And through sheer luck, we could actually use this little rule we just came up with on this triangle. Now, what I would not do is memorize this rule. What you should do is instead brush up on your algebra, because you need to be able to solve equations like this. If I'm dividing by something, you need to know that you can multiply to get rid of that thing that divides it. So let's say I want to do this using some of the information I have. I know one of my angles. I know my angle 34.5. So what I want to do is plug that in. I want to do sine of 34.5 degrees. I don't know my opposite side. That's what I'm trying to figure out. What is my opposite side? Well, if this is my angle, the opposite side of that angle is A. So whatever we chose for our angle, that defines for us which one is the opposite side. So in our case, opposite is this lowercase a. Let me pause this again.
Okay, what do you...
Sorry about that. Yeah, that's the other thing. People just like to walk in to my office after they knock. Okay, so the side opposite our angle is this lowercase a, and our hypotenuse, well, that's the same no matter what. Whatever angle we're using, the hypotenuse is still this 12.7, so I can plug that in. Whew, nothing like seeing my writing on video to make me realize how terrible it is. Okay, so now I've got something, and this is being multiplied here. So I'm going to calculate the sine of 34.5 degrees, and multiply it by 12.7, and that will give me my side there, A. Okay, so 12.7 times sine of 34.5 degrees. Oops. Now let me show you how I'm putting this in my calculator. I think I already showed you that, but again, since I'm redoing this video, it may have been in the other copy of this video. So I typed in sine of 34.5 in my calculator, and then I multiplied it by this 12.7. You could have done it the other way. You could multiply by 12.7 and then times 34.5. But this is the important part. Either way, you got to make sure. Oh, this is from glare. That you close this parentheses. Let me put it in there without the parentheses. So I type in sine of 34.5, and you notice it didn't close that parenthesis for me. I need to close that myself. I close it, and then I can multiply by 12.7. Okay, or again, I could have entered in the 12.7 first, and then times my sine of 34.5 degrees. And then it's actually, in that case, it'll actually work if I don't close the parentheses, but I always do it anyway. There's no reason not to. So I type that in and enter. I get 7.19. Okay. So we got A is equal to 7.19. Again, we only have 3 significant digits here. Now this is why significant digits are such a pain, and I normally don't count off for y'all when you do them. If we use this number to calculate this, our answer is not going to be it's not going to be as accurate. If you want to keep using this number in your calculations, you need to keep a few more significant digits. Now, your final answer should only have 3 because this only has 3, this only has 3. That means our final answer has to have 3. But if I was to use this, let's say I was going to use the Pythagorean theorem next, and use the Pythagorean theorem along with A, C, and B here to find this B. This is not going to give me a perfect answer. It's not going to give me as accurate an answer. I would need to keep a few more of these digits. Like I've got, what, 3, 3, 5, 9. That's way more than I need, actually. I would do 33, 5, 9. If you're going to continue using this in your calculation, you got to keep a few more digits, and then later on we'll, in our final answer, we'll eliminate those. That's why I don't like to make a big deal out of significant digits on your homework and stuff. I've had instructors that did that. It's just I don't know. You should be focusing on things that matter, like learning your trig functions, not so much on these details. Okay. Oops. So how do I want to find B? Like I said, I could use the Pythagorean theorem. I kind of feel like I should here. We got a lot of options. I could use this. I could use the cosine of this. The cosine relates to my adjacent side to the hypotenuse. I could do that. That's a really nice option because it doesn't use this one. Doesn't use this imprecise measurement. I could use the tangent. The tangent relates the opposite side to the adjacent side. But again, I'm in that kind of sticky situation where I'm using this number when I could avoid it. Now, there are going to be situations where you can't avoid using that number you've calculated, but when I have the opportunity to avoid it, I just avoid using it. What else could we do? We could find our angle first. That was actually really easy to do. Remember, the sum of these two angles has to be 90 degrees. So that tells me B is really easy to find. This uppercase B is going to be 90 degrees minus 34.5 degrees. Can you read that? No, you can't. Let me just bring this back a little. It's kind of a stretch. Oh, I write much better when I'm standing, I guess. So 90, 90 minus this 34.5. That gives us our measure of angle B. And what is that? It's going to be 60, 50, 55.5. I think it's going to be 55.5. 55, 65, 75, 85, 89, 90. So that would do it. So that tells me this one, 55.5 degrees. Okay, really I should use, this is kind of a, going back to those geometry rules. I never do it. I can never remember to do it. But really, we should use like different symbols for these different corners to show that these aren't the same angle. But I mean, I don't think anyone does that in trig. I normally don't remember to. Okay. That's just some messy work. I need to work on that. So we're still left with this problem of finding B. Now I could use, since I've got this angle 55.5 degrees, I could use that to measure my, and along my side to do opposite over adjacent. So I could do that. So I feel like doing what? I feel like using the Pythagorean theorem. We could use a trig function. You're probably more familiar with Pythagorean theorem. I feel like doing it at least once. So we're going to do the Pythagorean theorem. Okay, so the Pythagorean theorem says a squared plus b squared has to equal c squared. I know some of these values. I know a, 7.193359 squared. I don't know b, so I just leave that as b. And I do know this c, it's 12.7 squared. So notice I did use all those digits, the 7.93359. I used all those extra digits, and now I just need to work this out. Now let's see. I don't know. I'll just do this one step at a time. 193359. And I'll square it. So I square this first one, I get 51.7444. 1, 2, 3, 4, 5, 6. Yeah, I'll just leave a big old mess of them. But remember, at the end, we're only going to have 3 of these significant digits. Okay. We still don't know B. We're working on that. 12.7 I can calculate pretty easily. 12.7 squared, my calculator. 161.29. And then I just subtract. So on the left, that cancels, and I've got b squared. On the right, that cancels. We do that subtraction and get 109.5456 degrees. No, not degrees, because we are measuring a distance, not an angle. So last step, we've got b squared. How do we find b itself? We take the square root of both sides. Okay, so square root of b squared is b. I know you're somewhere saying it's plus or minus b. That's a tough question for us to get into now. The easiest way to explain it is to say, that while mathematically we take the square root of a variable squared, you have 2 options there, plus or minus that variable. But we're measuring a real world distance. This triangle, this is a real thing. We want the positive answer here. Later on, we'll talk about using negative as direction, and really that's a kind of an abstraction. It's kind of a higher order process. In physics, you do that a lot. When we get to vectors, we'll talk about using negative to indicate direction. And here, we don't have any coordinate system. We just have this triangle. We just want the positive result here. So 109.5456. I can take that square root in my calculator. 109.5456. And I get that this is 10.46640.339, all these digits. But now this is my final answer. It's actually the last answer in the problem, so I'm just going to write it as 10.4. No, 10.5. So I've got to have 3 significant digits, just like they gave me to start with. So that would be 3. But this 6 tells me to round that 4 up. So 10.5. And there we go. 10.5 what? Well, our original measurement, if you see on your screen there, the original measurement was in inches. So these are also inches. Or are they? No, they are. This one I'm not actually going to solve, but I wanted to kind of talk about this process. Here they gave us the length of a side and they gave us the hypotenuse. Oh, maybe I will. In fact, I will do. I'll start you off on this one. This one's a little different. First off, they didn't draw a triangle for you. So what you do, the first thing you should do is draw the triangle yourself. Because trying to do this without a drawing is more work than you need to do. You can label it or not. I'll go ahead and leave this thing labeled. I say that as I erase all my labels. Okay. So I'll also use A, B, and C. The advantage of drawing your own triangle is you can draw it just the way you like it. I know some people, because I've had students tell me that they like to draw their triangles like this, with their A, the one their angle they're interested in, bottom left corner. Whatever, you do it however you want. So what do they tell us? They said it has one side of length 29.43 centimeters. Which side? Well, I'm assuming they mean one of these two sides, since they gave us the hypotenuse. They say the hypotenuse is 53.58 centimeters. So we pick one of these and call it our side. So I don't care which one we pick. I'll pick the bottom one just to mix things up a little bit. So we said that side length is 29.43 centimeters. Okay, so I'll do this first part at least because this is slightly different than what we've done before, but we're not going to work through this whole problem. The rest of this is just like the last one. Now, what's different about this one is we don't have our angles in here. We don't have either of these angles, but we can find that really easily, again, using the trig function. So we want to pick a trig function that relates our two sides together. Now, depending on which angle we decide we want to find, that will tell us which trig function we want to use. So let's say, for example, we want to pick this angle. We like A for some reason. Let's try to find A. So we're going to call that theta. You can call it whatever you want. We call it A. It is A. I don't know why I'm mixing up the name. So we're just going to use the variable A for now. Why introduce a new variable when you don't have to? So this is A. I just moved my label in there. Whatever, it didn't matter. So what relates A to these two sides? Well, this is it's adjacent to A, and that's my hypotenuse. What relates the adjacent side to the hypotenuse? That's your cosine, right? So I would say the cosine of A is equal to my adjacent side In fact, I'm actually going to write out adjacent. I say I'm going to write it out. I'm going to write out ADJ. It's equal to the adjacent side divided by the hypotenuse. Oops, okay, but we know the adjacent side, and we know the hypotenuse. Okay. Okay, so now we've got that, we've got those numbers in place. The question is, how do we solve this thing for that variable a? It's got that cosine in front of it. And what you're going to have to remember here is, again, going back to algebra. Most of the trouble people have in trig is not related to trig. It's related to not being really comfortable with algebra. But it's okay because you can. I mean, some of these concepts you can still do this work without having a full mastery of the concept. But I will write it out for you over here. This is this goes back to the notion of inverses. And let's see, where can I do it? I'll actually do it right here. I've got some room here on the board. If I've got some function, if I want to get rid of the function and uncover just this x in the middle, what do I do to that function? Well, I would have to take the inverse function of it. This is one of the, depending on how it's defined, this could be the definition of your inverse, that this has to spit back out your original variable. Depending on how you define it, this could just be a property of the inverse function. So this is the great thing. If you plug an original function into the inverse, it spits back out your variable. So how does this work? We would do this by, we're going to apply the inverse function to both sides of our equation. So let me give you some crazy example before we start off. If I had given you, say, oh gosh, this is going to be awful. No, I could do this. Do I want to get into the whole discussion about this? I kind of do, and I kind of don't. Yeah, I'll give you a quick start here. The function f of x, let's say it's the squaring function. We don't even need the variable here. We don't even need this. We could say f of whatever means we take whatever and square it. Okay. Well, what is the opposite operation? What operation undoes squaring something? Well, if we can figure it out, we found our inverse. F of whatever. What would be the opposite operation of squaring something? I imagine, you can guess that it is the square root. So I'll actually write this with our variables in there. F of x is x squared. F inverse of x is square root of x. So now you can see what happens when I take the inverse function of both sides. What that means is I'm going to be taking the square root of this function, the square root of x squared. So what is f inverse? Of f of x? Well, that's f inverse of x squared. So what I did is I took my f of x, that's plugging into my inverse, and I replaced it with x squared. So that's all I did here. And I took f of x, I replaced it with what f of x is equal to. It's x squared. So instead of f inverse of f of x, I have f inverse of x squared. But what is f inverse? That is the square root function. So we've got the square root of x squared, and that spits back out x. Okay. So that was a really complicated explanation. Again, that's the kind of theoretical background to calculating an inverse of a function, and that spits back out your variable. Don't worry if that was too confusing, because it is to most people. Functions are kind of an abstract concept. It takes a while to get that stuff. And I'll write it that way. I'm going to write this step out where I take the inverse of both sides. But then the step after that, that's the one that every trig student I've ever seen actually uses. But I got to show you this. I got to show it to you this way at least once. So what I'm going to do is I'm going to take the inverse function of both sides, cosine inverse of cosine of A is equal to the cosine inverse of 29.43 over 53.58. Okay, but I don't know anyone who actually writes out this step other than me. And I don't write it out when I'm doing this on my own. I just write it out when I'm explaining this stuff the first time. Because why not complicate things the first time? Now we saw this, when I take the inverse function of my original function, it cancels out my function. It spits back out this variable. And I haven't been using parentheses here. That's a habit that I try not to get into, because it always annoyed me when people change things up. So I'm making the cosine of my variable a, cosine of a, okay? When I take the inverse function of that function, it leaves me with a. Now, if you're terribly lost, what I suggest you do is ignore the past 5 minutes, and when you see this, you've got this thing. You've got just numbers on one side. You've got your trig function of a variable on the other. Skip right down here. That variable is the inverse function of this. So cosine, the inverse function is inverse cosine of whatever your number is, 29.43 divided by 53.58. Okay, and now that's something you just plug in your calculator. So again, if you didn't like this explanation, if you didn't like any of the stuff about inverses, you just ignore that one. I do like to show it at least once. It seems a little blurrier than it was last time. All right, now again, this is something you can punch right into your calculator. If you look on your calculator, you should have a cosine button, right? Right above that cosine button is the cosine inverse, that blue, that light blue. In order to get to that, most calculators have like a second function or an option function or something. I'm going to punch that, and then this cosine button, and that will give me the cosine inverse. And then I just plug in my numbers as usual. 29.43 divided by 53. Yeah, I'm making all kinds of errors. Divided by 53.58. Now make sure when you're entering that, you do your division. You put all of that inside your parentheses. So only after you've typed in all your numbers, then I'm going to close up my parentheses. Okay, because I'm calculating that fraction, and then I'm going to take the function of it. So that gives me cosine inverse of that fraction is 5.66. That doesn't seem right. Oh, it's 56.68. Okay. We can only have 4 significant digits in this, but because you may use this elsewhere in your calculations, I would leave a few more. So I use a different color, 2, 9, 0, 8, 5, 6. So if you're going to continue, or you think there's a chance that you're going to use these digits later, you need to write the rest of them down. And this is degrees here, right? Because this is our angle. A is our angle there. Wow, what a mess. Okay, so that gives us this A. Now over here, here's where I'm writing my final answer. So I'm going to write down just the 4 digits there. 56.68. Now I'm not going to finish this problem out. You can find this one using your Pythagorean theorem. You could use one of your trig functions. Now that you know this angle, you could say use the sine function. Sine is the opposite of the hypotenuse. You could use that to find that opposite side. So if we label this lowercase a, we could do that pretty easily. Sine of 56.68 degrees has to equal a divided by our hypotenuse. You could then multiply this by 53.58 degrees, and that tells you what your lowercase a has to be. But again, when you actually do this calculation, you should be using these extra digits here. Let me see, I'm going to have to erase that and make room for those extra digits. Let me clean this up a little bit. Get that out of the way. Okay. So I'm only left with this part. So this would be sine of 56.68. I'll just use a few more of these digits. 291. That should probably be sufficient. But again, I just don't want to use too few digits here. So I'm going to carry in a few extra for my calculation. That's how I would start this. So what is your first step? I'll give you a second to think about it. What is your first step here? You can even pause the video, take a look at it. Okay, moving on. If we've got our variable divided by some number, we want to solve it for our variable, just multiply by this number. Okay, and that gets rid of our number, and it leaves us with A. What is A equal to? All of this mess. Punch that in your calculator. That will give you A, and we're almost done. You would just need to find your last angle, B. But you could do that pretty easily. 90 minus 56.68. So I won't continue this out. He's already going pretty long. Last thing here is angles of elevation and angles of depression. What these are the angles you make with the horizontal, I just say the horizontal, or a horizontal line, something that is parallel to the ground, even though our ground isn't really horizontal, it's curved. So an angle of elevation is if you're looking up from horizontal, it's whatever that angle is between the ground and looking up. Angle of depression is like you're standing on a cliff and you're looking down. Again, it's that angle from the ground, from a line parallel to the ground, looking down. That's your angle of depression. The only thing I want to point out in these problems is you got to be careful to take into account where you're measuring from. Other than that, this is our standard solving a right triangle type problem. So like this example, Pat Porterfield, she's standing 123 feet from the base of a flagpole. I guess she like paced that out or something. She knows the angle of elevation, so I guess she's like using a sextant or something to view the top of that flagpole. That's really all we need for this first part. You've got a right triangle there with our angle 26.3 degrees and that distance to the flagpole. You could use that to find this height of the flagpole there, that part A. But what you have to remember here, her eyes, she's not laying on the ground. She's measuring from wherever her eye level is, from 5.3 feet. So whatever she gets here for this leg, you need to be careful. Make sure you add that extra 5.30 feet to it, and that would give you your final height. So that's the only word of warning I have for these. Other than that, it's standard solving a right triangle situation. So that's it. I know this has been a real kind of pain getting all this started up, but I think we're just going to start uploading these to YouTube. So